Next speaker is Professor Anita Tomar from Government Degree College, Thatyur, Uttarakhand. She will talk about geometric properties of non-unique fixed points and applications. Okay, so yeah, I request Professor Anita to start.
So thank you so much. So today I'm going to talk on geometric properties of non-unique fixed points and applications. So one of the significant outcome of the fixed point theory is when a map under minimal suitable conditions have a fixed point. But it is not always possible to have a fixed point. There may exist a unique fixed point or there may not exist a fixed point. But if a fixed point is non-unique, then the set of non-unique fixed points may form a circle, a disk, or an ellipse and have several applications in biology, neural networks, economics, and artificial intelligence. So actually, ellipses emerge naturally in numerous areas, for example, planetary orbits. And we know that ellipse is the locus of a point, which is the sum of Euclidean distances from the two foci is constant. And we may also look ellipses as the flattened circles. So in this talk, first of all, we familiarize fixed ellipse, and then we discuss the geometric properties of the set of non-unique fixed points of a discontinuous self-map in reference to fixed circle problems. So first of all, we will discuss some shapes of the ellipses with different lengths of semi-major axis and different foci and in different metric spaces. So the ellipse having focus at C1 and C2 and length of semi-major axis at A is defined as set of all the points W belonging to the metric space MD such that its sum of its distance from the two focus is equal to 2A, where A is nothing but a positive real number. And the midpoint of C1 and this all we know that midpoint of the line C1, C2 is the center of the ellipse. And the line joining C1 and C2 is the major axis and the line perpendicular to it is the minor axis. And the distance between the two focus is the linear eccentricity of the ellipse. And sin f upon sin A is the numerical eccentricity. So we can see circles as the ellipses of vanishing eccentricity in which both the focal points are same. So if we define a usual metric on the set of real numbers, and if we take one focus at -2, another focus at 2, and we take the length of semi-major axis as 5, then we see that with reference to this metric, the ellipse is equal to the set of points -5 and 5. But if we consider a two-dimensional real space and define a metric as under root W1 minus V1 square plus W2 minus V2 square, and if we consider one focus at 2, 0, another focus at 0, 2, and if we take the major axis, length of semi-major axis as 2, then the equation of ellipse centered at 1, 1 is nothing but under root 2 minus W1 square plus W2 square plus under root W1 square plus 2 minus W2 square equal to 4. But if we define the metric as modulus of W1 minus V1 plus W2 minus V2, and we take the same center and same focus as in the previous examples, then the equation of ellipse is modulus of 2 minus W1 plus modulus of W2 plus modulus of W1 plus modulus of 2 minus W2 equal to 4. And if we draw the diagram of these examples, then we see that this blue line is the ellipse corresponding to the metric under root W1 minus V1 whole square plus W2 minus V2 whole square. And if this green line is the ellipse corresponding to the metric W1 modulus of W1 minus V1 plus W2 minus V2. And this orange line is the ellipse corresponding to the metric maximum of W1 minus V1 modulus W2 minus V2, and center of these ellipses are at 1, 1, and one focus is at 0, 2, another focus is at 2, 0. If we define a metric as dWV equal to modulus of W1 minus V1 plus W2 minus V2, and if we change the length of semi-major axis, then we observe that the ellipse with length of semi-major axis as A equal to 2, and the center of this ellipse is 1, 1. One focus is at 0, 2, another focus is at 2, 0. Then for A equal to 2, this green one is the ellipse. If we change the length of semi-major axis to 2.5, A equal to 2.5, then this blue one is the shape of the ellipse. If we change the length of major axis, semi-major axis to be A equal to 3, then this is the orange one is the shape of the ellipse. And if we again increase the length of semi-major axis to be A equal to 4, then this pink one is the shape of the ellipse. Again, if we define the metric as maximum of modulus of W1 minus V1 and or the W2 minus V2, and for A equal to 1, 2, 3 means these are the length of semi-major axis. This is for A equal to 1, A equal to 2, and A equal to 3. The center is at 1, 1, and one focus is at 0, 2, another focus is at 2, 0. Then these are the different ellipses. And if we keep the focus fixed, no, if we change the focus and length of major axis is semi-major axis is 2. So if the one focus is at 0, 2, another focus is at 2, 0, then this is the ellipse with reference to the metric defined as dWV equal to modulus of W1 minus V1 plus W2 minus V2. If the focus is one focus is at 3, 3, another focus is at 4, 3, then this pink one is the ellipse. If one focus is at minus 3, minus 2, another focus is at minus 1, minus 2, then this is the ellipse. If one focus is at 3, 0, another is at 5, minus 2, this down one is the ellipse. So we observe that shape of some ellipses may change on changing the length of semi-major axis or foci. So first of all, we introduce fixed ellipse. If we define an ellipse with one focus at C1, another focus at C2, and A is the length of semi-major axis, and if we define a self-map A of a metric space MD as, and take AW equal to W, means W is a fixed point of A, for all W belonging to this ellipse, then this ellipse is called the fixed ellipse of A. A is the self-map, and this is the ellipse. Means if AW equal to W means every point of A is a W is a fixed point for the elements of for elements on the ellipse, then this ellipse is called the fixed ellipse. So if this is the ellipse on the metric space MD, and if we define sigma from M to 0 infinity as sigma omega equal to dC1 omega plus dC2 omega, where C1, C2 omega are the elements of M, and we take these conditions, we define these postulates for our theorem. In that case, this ellipse will be the unique fixed ellipse for A. And these conditions are indispensable for the existence of unique fixed ellipse. If any one of this condition is not satisfied, then in that case, the ellipse will not be a fixed ellipse. So the geometrical one, we will see that the first condition show that this point AW is in the exterior of ellipse, and second condition show that AW is in the interior of the ellipse. If we consider a two-dimensional space, and if we define a metric as W1 minus V1 whole square plus W2 minus V2 whole square, and then the ellipse having focus at minus 30 and 30, and length of semi-major axis 5 is nothing but W1 square upon 25 plus W2 square upon 16 equal to 1. And if we define a self map, AB equal to AB, for which AB belongs to 5 cos theta to 4 sin theta, and CD otherwise, then in that case, distance between AB and CD will be less than 1 upon 10 d omega W. So one may verify that all the conditions of our theorem are verified, and in this case, this E with focus C1 and C2 and length of semi-major axis 5 is a unique fixed ellipse. Or we can say that non-unique fixed point of this self-map A contains a unique ellipse having focus at C1, C2 and semi-major axis 5. I have skipped the proof of the theorem because there was a limitation of time. So this is the diagram. Blue lines demonstrate the ellipse which is fixed by the function A. And this is the unique fixed ellipse. And in this example, we show that all the conditions which we have assumed in our theorem 1 are necessary for the existence of unique ellipse. If we define a metric dWV equal to modulus of W minus V, and if we take the focus at one focus at 1 and another focus at 2, and we take length of semi-major axis as 2.5, then we have the ellipse minus 1, 4. And if we define a map like this, it is equal to 1 for the points on the ellipse and minus 1 otherwise, then one may see that A verifies only the first condition of theorem 1 and does not satisfy the second and third condition. And also one may notice that A does not fix this ellipse. And in fact, it does not fix any of the ellipse. If we define a metric M equal to dWV equal to W1 minus V1 whole square plus W2 minus V2 whole square, and if we take one focus at minus 50, another at 50, in that case, the equation of ellipse will be W1 square upon 169 plus W2 square upon 144 equal to 1. And if we define a map as AWV equal to W0 for all the points for which W is greater than 0, and 0V for all the points WV is less than 0, then a self map A satisfies only the second condition but does not satisfy first and third conditions of theorem 1. And one may see that A does not fix this ellipse which we have defined on last slide, but it fixes only the points 13, 0, 0, 12 and 0, minus 12. If we take the metric as usual metric and the ellipse is defined like this, here 2 and 4 are the foci and 5 is the length of major axis, then in this case, the ellipse is nothing but the set of points minus 2 and 8. And if the self map is defined as minus 2 for all the points W between minus infinity to 2, it is closed at 2, and 8 for W belonging to minus 2 to infinity, then one may observe that A verifies all the postulates of theorem 1 except third. Third condition is necessary for the existence of unique ellipse. So in this case, one may see that this is the fixed ellipse of A, means non-unique fixed point of A contains this ellipse, but this ellipse is not a fixed ellipse, unique. This ellipse is not a unique fixed ellipse. There may exist infinitely many ellipses which are fixed by a self map A. If in theorem 1, we replace second condition by eta dWAW plus dC1AW plus dC2AW greater than or equal to 2A, then also the conclusion of theorem 1 remains true. And these are some of the examples which demonstrate that the conditions are necessary for the existence of unique ellipse. These are the similar examples. In this case, matrix is defined like this and map is defined like this. And we see that this is the shape of the ellipse, which is not same as the ellipse in the Euclidean plane. And the center of this ellipse is at is 0.52. Focus is at 0, 2 and 1, 2. And this is the blue line demonstrate the ellipse, which is fixed by the function A. And these are some of the examples which again demonstrate that conditions, first, second, third conditions of the theorem are important for the existence of ellipse, fixed ellipse or unique fixed ellipse. So I'm also skipping all these because we have a limitation of time. So we see that it is not necessary that an ellipse defined in a metric space is same as an ellipse in Euclidean space. Also, the shape of ellipse may also change on changing the center, the semi-major axis, or foci, or the metric. Or one may observe that semi-major axis A of the fixed ellipse does not depend on the center and may not be maximal. And if this condition is satisfied, it does not mean that this is a fixed ellipse. E C1 C2 A, the ellipse having focus at C1 C2 and major axis at semi-major axis at A is a fixed ellipse. For the existence of ellipse, fixed ellipse, we have defined that if AW equal to W for all the points W belonging to the ellipse, then only this is a fixed ellipse. For more work on the existence of fixed disk or fixed circle, one may refer to these papers. We have extended these works to fixed ellipse case. This is one proposition that if these are two ellipses having focus at C1, C2 and length of major axis A, another ellipse has focus at C1 dash and C2 dash and the length of semi-major axis at A dash, then in this case, there exists at least one self-map M on P such that M fixes the ellipse, these two ellipses. So following this pattern, we may extend this result to an ellipses also. Now this is one more proposition which show that in any metric space in which an ellipse contains all the points of a space except its foci and validate it by giving an example. Suppose we consider a point A in a set of real number and define a metric dA as 0 for if W equal to V and A if W is not equal to V. Then this E C1 C2A in this metric space where M is set of real number, metric is defined like this. Then in this case, it contains all the points W belonging to M except the foci C1, C2 belonging to N. Suppose MDA is the metric space, so that the metric DA be as in proposition 2.3. Consider the set J equal to Wi, where Wi I lies between 1 and N. Then obviously there exists an ellipse, in particular this ellipse consisting of the elements of J as follows, that it is the set of all W belonging to M such that the distance of W from C1 plus distance of W from C2 is equal to 2A. In this case, this is equal to W1, W2, W1. So this is the set of all the points except the focus. Now we will discuss the continuity of a self-map on a fixed ellipse. Suppose this is the ellipse, or in fact this is the fixed ellipse of a self-map A in a metric space MD, where the distance of AW and AB is less or equal to eta NWB, where NWB is defined like this. Suppose for epsilon greater than 0, there exists a delta greater than 0 satisfying this condition. Then in this case, if A has a unique fixed point, say U, which belongs to this ellipse, and limit of AWN as n tends to infinity is equal to U belonging to M, then a self-map A is continuous at an ellipse if and only if limit NW and U, W and U as W tends to U is equal to 0. Or in other words, we may say that A is discontinuous at an ellipse if and only if this limit is not equal to 0. So we know that the storage capacity of a discontinuous activation function is higher than the continuous activation function. So motivated by this fact, we discuss a Mexican hat type non-monotonic discontinuous activation function, which is used to introduce a non-linear properties to the neural network. So this is the Mexican hat type activation function, and we define a metric D as a usual metric. If we take the constants like this, then we get this activation function. Obviously, this is a discontinuous activation function, and one may verify that it satisfies all the properties of theorem 1 and theorem 2. It means it has a fixed ellipse. So the ellipse having one focus at 1, another focus at 2, and length of semi-major axis 3 is equal to -3/2 upon and 9/2. This is equal to this set. Hence, A fixes this ellipse. So if we calculate the limit of NW -3/2 as W tends to -3/2, it will come out to be 0. And if we calculate the limit of NW 9/2 as W tends to 9/2, it is also equal to 0. It means A is continuous at the fixed point -3/2, which belongs to this ellipse, and 9/2, which also belongs to this ellipse. It means the function is continuous at the ellipse. So this is the diagram of the Mexican hat type discontinuous non-monotonic activation function, and one may observe that this function is continuous at -3/2 and 9/2. This is -3/2, and here it will be somewhere here it will be 9/2. So if we take the values like this, in that case also we get the discontinuous activation function, and one may observe that this discontinuous activation function satisfies all the postulates of both the theorems 1 and 2, and for the ellipse having focus at 6 and another focus at 7, and length of semi-major axis at 2.5, and this is equal to 4.9. So if we calculate the value of NW4 as limit W tends to 4, then this limit is not equal to 0. And if we calculate NW9 as W tends to 9, then this is equal to 9. So it means A is discontinuous at the point 4 belonging to the ellipse having one focus at 6, another focus at 7, and the length of semi-major axis as 2.5, and is continuous at the point, at the fixed point 9 belonging to the ellipse, the same ellipse. It means A is discontinuous at an ellipse 6, 7, 2.5. So one may observe from this figure, this is the Mexican hat type discontinuous non-monotonic activation function, and here the values were 4 and 9. So it is discontinuous at 4 and continuous at 9. It is discontinuous at 4 and continuous at 9. So clearly Mexican hat type activation function is never monotonically increasing. So using NWB, we may decide the fixed point at which the activation function is continuous or discontinuous. Researchers show that the maximum human deaths on the earth are due to the heart disease. So ECG signal classification is significant for early diagnosis and treatment of cardiac diseases. Consequently, a wavelet neural network model is considered to be good for making neural network more efficient. So it is worth mentioning here that maps having fixed points, fixed circles, or fixed ellipses have been utilized in neural network as activation functions. So our results may also be useful to neural nets under some suitable conditions. So I conclude by saying that we have explored a new direction to the geometric properties of the set of non-unique fixed points of a discontinuous map via fixed ellipse. Also, we have obtained the application of fixed ellipse to discontinuous activation function on metric spaces. It is interesting to mention here that the activation function which have the fixed ellipse for a complex valued neural network give assurance of the fixed of the existence of fixed points of the complex valued fulfilled neural network. So for detail, one may refer to this paper. So these are some of the references if anyone is interested, and the results of this talk may be extended to some other spaces like S-metric spaces, F-metric spaces, partial metric spaces, and so on. There are so many metric spaces existing in the literature. So we may extend these results to different spaces. Thank you for your kind attention. Thank you so much.
Okay, is there any question or comments?
I just had one comment that, there, if you are in R2, then circle will be isomorphic to ellipse in by some function. Then one can transfer all these theory from circle to ellipse and back, right?
Yeah, maybe try. Maybe try. Yeah.
And same thing, then triangle, hexagon, pentagon, everything can be done. So,
but it's not been explored right now. But of course,
but is there means? So you could have a general theory. Why have just this circle and ellipses?
Pardon?
Why have it only for ellipse or circle? Because I mean, it's all these shapes are just closed curves, so they are isomorphic. Actually, at least the ones I'm mentioning.
Actually, it depends on the set of non-unique fixed points which we are considering. So maybe there may be different shapes, but of course, till now,
you're only changing the metric, right, and getting different shapes. So that would be similar theory because you would have a map from one to the other. So anyway, thank you.
Yeah, I put up certain things on chat. There is Browder fixed point theorem for convex compact sets. And since she considered mainly vector spaces, normed spaces, that will apply Browder fixed point theorem. And moreover, fixed point theory was built for integral equations and things like that with applications to solutions of differential equations. So I would like to see more literature or using or having applications to differential equations, integral equations, or something like that. And please read the remarks that I wrote on the chat.
Okay, thank you.
Okay, thank you.